Hello and welcome to lecture 4 of the course Theory of Computation. So this is going to be a short lecture, mostly going to be about the significance of regular languages. In lecture 3 we saw what deterministic finite automata were, right, DFAs, and then we defined regular languages as those languages that can be recognized by DFAs. So in this lecture we are just going to explain why it is important, right? So as we saw, DFAs are fairly simple rudimentary computing devices, right? So you have a state control, a machine which reads the input, and then it has some states, some of which are designated as accepting, right? So after you read the input, if you are in an accepting state, you accept the input. If you are in a non-accepting state, you do not accept the input. So a set of all strings that are accepted by a DFA constitutes the language of the DFA, right? Further, if there is a language, if there is for a specific language, if there is a DFA that recognizes that language, we say that that language is regular, right? So regular languages are a way to characterize the power of DFAs. So we want to understand what DFAs can do, right? So one possibility is that when you see DFAs, and when you see the different ways you can put them together, one may think that perhaps any kind of language, for any kind of language we can construct a DFA. But that, right? So we want to know what kind of languages can be recognized by DFAs and what kind of languages cannot be recognized by DFAs, right? So towards understanding that, we define the regular languages, and then we will see some properties. So for instance, we saw that regular languages are closed under complement, right? Meaning if a language is regular, the complement language, if A is regular, right? If A is regular, the A complement is also regular, right? So this is, if A is regular, then the complement is also regular, right? So, and what are the specialities of regular languages, or like how are actually the DFAs computing? How are the deterministic finite automata computing, right? So, for example, let's take this one DFA that we saw in the previous lecture. This accepts all the strings which for which the number of ones is a multiple of 5. Right. So if your string is has let's say 5 ones, it accepts. So right, for instance, this string is accepted because it has 5 ones. If it has 10 ones too, it will accept. Right. So now it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ones. Right. So 4, 5, 6, 7, 8, 9, 10 ones, right? So even this is accepted. So as long as the string contains the number of ones contained by the string is a multiple of 5, this is accepted. So let's see what this machine actually doing, what this machine is doing, right? So Q0 is accepting state, meaning after reading any string that for which the number of ones is a multiple of 5, you will end at Q0. If the number of multiples is let's say this string, right? So let me erase the previous string and let's consider just this string, right? Where does this string end up? So the first one will take you to Q1, second one will take you to Q2, third one will take you to Q3, and it will remain there. So Q3 is the state where all the strings which have 3 ones end up. But Q3 is also the state where all the strings that have 8 ones end up, right? So Q3 is the state where as long as you have 3 ones, 8 ones, 13 ones, so as long as the number of ones is a multiple, not a multiple, leaves a remainder of 3 when you divide by 5, you end at Q3. So, or in other words, if the number of ones is 3 modulo 5, you end up at Q3. And similarly, if the number of ones is 2 modulo 5, you end up at Q2, right? And so on. Similarly for Q1 and Q4. So what is happening here is these states Q0, Q1, Q2, Q3 and Q4 are being used to keep track of the count of the number of ones with the modulo 5 condition. So it is like, so if you want to actually count the number of ones, you need a lot of states, you need an infinite states, but as long as you need to count only the remainder when you divide by 5, this machine would do. So here what is happening is that the states are being used as the counter here. So in other words, the states are being used as the memory here. So if you look at any DFA that you built, similarly we would have, each state would be like trying to have some role. So each state would be trying to identify a certain number of or certain subset of the strings that that are processed by the DFA. So this is how in the case of this particular DFA the states play a role. And similar, if you take any DFA, so and you should be able to analyze and see which are the strings that end up at each state, right? So this will give you a lot of insight about how the DFAs operate. And just as I mentioned earlier, not all the languages are regular, right? So it's only a special subclass of languages that are regular. For instance, this language that is written over here, right? So it's a fairly simple language, right? It's easy to describe. It first contains the empty string, then the string 0, 1. So I'm talking about this language. It first contains the empty string, then the string 0, 1, then the string 0, 0, 1, 1, then the string 0, 0, 0, 1, 1, 1, then the string 0, 0, 0, 0, 1, 1, 1, 1, and so on. So it's an infinite language, but the pattern is very clear, right? So it's easy to describe. I just told you what it is. And basically there are some number of zeros followed by the same number of ones, right? This happens to be not a regular language, right? So you can think why it is not a regular language. Maybe it's even better if you just try to construct a DFA for it and then you see why you are not able to do it, right? So you will fail because I'm telling you so, because it's not regular. So you should not be able to construct a DFA. So you can try to construct a DFA that may give you some insights onto as to why this language is not regular. So it's a fairly simple language, right? So the point is we want to understand what is regular, what is not regular, and what are the structure of the languages, right? So what if a language is regular, what properties does it have, right? So for instance, we already saw that regular languages are closed under complement. So the next part, the next lecture, we will see regular operations and we'll see closure under that, right? Right. So what are regular operations? So regular operations are fairly simple, straightforward operations. So three operations are defined. One is union, which is just the setwise union. So if A and B are two languages, the union of these two languages is a setwise union. So the set of all strings that are either in A or in B, right? Two, concatenation. Maybe it's easy to go with the example. So if suppose A is the language good and comma bad, right? So if A is the language good bad and B is the language boy comma girl, the alphabet is all the English alphabet, then A union B is simply the string good followed by the string bad followed by the string boy followed by girl, right? So these are the four strings that constitute the union language. Basically it's the setwise union. So what is concatenation? Concatenation is the set of all strings that are formed by concatenating a string of A with a string of B in that order, right? So concatenation respects the order. So A concatenation B means you take a string from A, append a string of B to that. So string of A followed by a string of B. So A concatenation B need not be the same as B concatenation A because the orders are changed. Right? So let's see what is A concatenation B in this case. So A is good bad, B is boy girl. So A concatenation B is good boy, good girl. Sorry, there is no space. Sorry. bad boy followed by bad girl. Right, so these are the 4 strings in the concatenation language. So good appended by boy, so where good is from A, boy is from B. Similarly, good followed by girl, where good is from A, girl is from B. Similarly, bad boy and bad girl. And finally, the star operation is similar to the Kleene star that we defined earlier, where we defined it for alphabets. Here we are defining it for languages. So A star, where A is a language, is basically it's basically x1 x2 up to xk concatenated together. So it's k strings concatenated, where each x1 x2 x3 x4 xk, all of them are belong to A, right? Each of them belong to A. X1 belongs to A, x2 belongs to A, everything belongs to A, and k could be anything. K could be 0, k could be 1, k could be 2, k could be 3. So k could be any finite number, right? So k could be any finite number, right? So let's see. So what is so for instance, when A is the language good comma bad, right? So A star contains the following. So first of all, k can be 0 also. So k can be 0 means no string is there, which means it results in the empty string. Then k could be 1, where you just have one string x1, which belongs to A, right? So the strings that belong to A are good and bad, and set of x1 x2 where k is equal to 2. So 2 strings where it belongs to A. So it could be good good, it could be good bad, it could be bad good, it could be bad bad, right? So these are the 4 possibilities of writing x1 x2, where x1 comes from A followed by x2 also coming from A. x1 and x2 need not be the same, it need not be different, it could be the same, it could be different, right? So that's why there are 4 possibilities. Then let's go to the case when k is 3. So when we have x1 x2 x3, where each one of them come from A. So let's start with good good good, then followed by good good bad, and good 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 bad bad, and so on, right? So then at the end you will have bad bad bad, right, followed by and so on. So right, so again this is an infinite set, because k could be 1 2 3 4 5 6, it could be any number, 100 1000 and so on, right? And A star is an infinite set, just that a finite number of strings from A are connected together to form a string in A star. So this is just an example. So we took two languages A and B. We saw the union, what the union is, what the concatenation is, and what the star of A is. As an exercise, you can work out. So as an exercise, so work out B star. You can try to write down what B star is. So notice that epsilon, the empty string, is also part of A star. So like I said, we already saw that regular languages are closed under complement. And then in the next coming lectures, we will see that regular languages are closed under regular operations as well. Meaning, if A is regular and B is regular, A union B is regular. If A is regular and B is regular, A concatenation B is regular. And if A is regular, A star is regular, right? So we will see all of that in the next lecture. and or not all of that, some of that. So that's it. So we briefly explained the significance of regular languages, how computation happens through states, and we said why all languages are not regular, and hence there is it is interesting to see which ones are regular and which ones are not, and what properties do regular languages have. And so these closure properties become interesting for the same reason, and hence we explained that regular operations, right? So regular operations are 3 operations on languages, and we said that regular languages are closed under regular operations without proof, and we'll see the proof in the coming lectures.